A galvanic cell is an electrochemical cell in which a redox reaction occurs, and the redox reaction is spontaneous. Now, on the screen there you see that there is an anode and a cathode, and notice that the electron flow is from the anode to the cathode through the wire and external load. Now, the external load could be a light bulb that you put in there, and as the electrons flow from the anode to the cathode, they will light up that light bulb. Now, notice that the anode is described as the electron-rich electrode. That's where the electrons are going to come from. And then the cathode is the electron-poor electrode. That's where the electrons are going to go. Notice also that at the anode, that's where oxidation takes place, and notice at the cathode, that's where reduction takes place. Notice too, there's a porous partition there in the middle. That porous partition there is allowing for the circuit to be complete, and also allowing for charges to move through that partition to kind of make it so that there's no charge buildup on either side of the electrochemical cell. Now, in order for the reaction to be spontaneous, it must have a positive cell potential. And as we've stated before, for a reaction to be spontaneous, it must have a negative delta G. Now, we're going to discuss how to calculate the cell potential of a specific electrochemical cell, and we're also going to talk about how to determine the delta G of a specific electrochemical cell. So let's take a look at the most common galvanic or electrochemical cell, and that's the zinc-copper cell. Now, from a table of reduction potentials, we can actually look up the voltage, and remember this is a voltage relative to hydrogen being 0. We can look up the voltage for the zinc reaction and the copper reaction. And what we want the two reactions to add up and give us a positive overall voltage. Notice that both of these reactions are written in terms of reduction. So what we will have to do is determine which one is going to be the oxidation reaction. And we do that by determining what combination of the two will give us an overall positive voltage. Because right now, if you add those two together, of course, you're going to get a negative voltage, and you also will not have an oxidation and a reduction. So let's take the two of them and let's try adding them together. The less positive or more negative of the two becomes the oxidation. So it looks like we have taken the zinc reaction and we have flipped it. So we've kept the copper reaction the way it was, 0.34 volts, so that's our reduction. And then we've taken the less positive. Remember that in the previous slide the zinc reaction was written as a reduction and it was a negative 0.76. So we have flipped that. It is now our oxidation. When we sum up the two voltages, then we get an overall voltage of 1.10 volts. So therefore we've determined by taking one of the reactions and making it an oxidation so that the total sum is positive, we've determined which reaction is the reduction and which is the oxidation. And then notice up in our cell, the zinc is at the anode because that's oxidation. So you see electrons being lost there and traveling through the external source. And this time the external source is a voltmeter, and that voltmeter is going to register a voltage. And it's going to travel through the wire, and the electrons are going to be captured at the cathode and cause the copper plus 2, of course, to form copper metal. So what you would eventually see then is the zinc anode in the left. You would see the mass of that would gradually decrease, and on the right side in the cathode you would see the copper cathode actually would increase in mass. So again, zinc, copper, galvanic cell, we've determined the oxidation, we've determined the reduction, and then that allows us to take a look at the actual cell and determine the direction of the electron flow. Now, typically, when we describe a cell, we use something called a line notation. The line notation looks like this, and generally we put the anode material first, and then the anode solution second, and then a cathode solution next, and then the cathode material. So whatever the anode is made out of, that goes first. The anode solution, a double line usually to separate the two half cells, then the cathode solution, and then the cathode material. So this is how you would denote or label the copper zinc electrochemical cell seen above.